Section: Introduction. In this section, we discuss the impressive capabilities of today's large foundation models, which often match or surpass human performance on various tasks. We anticipate that in the near future, models will be even more powerful than humans, potentially achieved through a careful mix of supervised and reinforcement learning. This raises the question of superalignment. As these models become more intelligent, can we still effectively guide them to align with human values? To explore this, we introduced the concept of weak to strong learning, which allows us to study superalignment even before superhuman models are available. In our approach, we use a weaker teacher model, like GPT-2, trained on specific tasks with accurate labels, simulating a human with some expertise. We then use this teacher to label data for a stronger student model, such as GPT-4. Surprisingly, we found that the student model often outperforms the teacher, despite the teacher's imperfect labels. This suggests that the student can grasp the task's essence even with flawed guidance. However, we must be cautious. A key aspect of our setup is early stopping during training, as overtraining the student can lead to it mimicking the teacher's mistakes, resulting in no improvement or even worse performance. We found that stopping at the right moment significantly enhances weak to strong generalization. Yet, we still need to understand how broadly this phenomenon applies and what factors influence it. For instance, does it require advanced models like GPT-4, or can simpler models also exhibit this behavior? Additionally, we question whether scaling up model sizes will improve or hinder weak to strong generalization. In our paper, we demonstrate that weak to strong generalization can occur even in simple models, specifically random feature models, which are two-layer networks with a random bottom layer and a trained top layer. We analyze a scenario where the teacher and student models have different numbers of units, with the student being significantly stronger. We train both models while keeping the bottom layer fixed and assume the teacher model is well trained, achieving minimal population loss. The only remaining error comes from the limitations of the model size. Our contributions include analyzing how weak to strong generalization can happen in random feature models when the student is trained using gradient descent with early stopping. We rigorously prove that the student can achieve a much lower error than the teacher, potentially as small as a power of the teacher's error. We establish that the performance gap between the models can be very large, indicating that the student can significantly outperform the teacher. We also show that for linear networks learning specific functions, the gap can be maximized under optimal training conditions for the teacher. Overall, we provide a framework to understand weak to strong generalization and identify the best early stopping time for a wide range of random feature models and target functions. Section Summary. In this section, we explore the phenomenon of weak to strong generalization, demonstrating that a stronger student model can outperform a weaker teacher model, even with imperfect labels, particularly when trained with early stopping. We provide rigorous proofs and insights into how this generalization occurs in random feature models, emphasizing the importance of optimal teacher training and the role of early stopping in mitigating errors. Section: Related Work. In this section, we discuss related work, focusing on asymptotic notation and its application in our context. We denote a multiplicative factor that depends on one or more variables. For any two quantities that may rely on various variables, we express that there exists a function and an exponent such that a specific relationship always holds. We explore learning a predictor using two-layer networks with random features, aiming for minimal population loss. Here, we consider a specific input distribution and a target function. Our models consist of two layers, where the bottom layer's weights are randomly selected from a fixed distribution and remain unchanged during training, while only the top layer's weights are adjusted. These models have been widely studied as finite approximations of kernel methods and in the context of deep learning. We examine two variations of the random feature model, differing in activation function and input distribution. The first model uses a standard ReLU activation function with bottom layer weights uniformly distributed over a sphere, and the inputs are also uniformly distributed on the sphere. We focus on even polynomial target functions in this setup. The second model employs a linear activation function, with bottom layer weights drawn from a standard Gaussian distribution, and the inputs are non-isotropic, coming from a Gaussian distribution with decreasing diagonal covariance. Here, we consider linear targets supported on the first few coordinates. Next, we establish weak to strong generalization, starting with the ReLU network. We analyze a target that is an even polynomial of a certain degree, normalized appropriately. If the student is trained with a specific stopping time, we find that with high probability, certain relationships hold as the teacher size increases. Under the Gaussian universality ansatz, we observe that for specific parameters, the student error decreases significantly faster than the teacher error, although the exact rate of this decrease is not fully captured by our current measures. We also demonstrate that in the ReLU model, the student error is polynomially smaller than the teacher error. Our experiments support this, showing that the loss ratio decreases as the teacher size grows, and the student loss is significantly smaller than the teacher loss, often exceeding our theoretical bounds. To further explore this separation, we turn to the linear network model. We analyze a linear target supported by the first few coordinates and find that, under the weak to strong setting, the student loss is quadratically smaller than the teacher loss for moderately sized networks. Our simulations confirm this behavior, aligning with the theoretical predictions we established. Section Summary. In this section, we explore the weak to strong generalization in two-layer networks with random features, focusing on different activation functions and input distributions. We demonstrate that, under certain conditions, the student model can achieve significantly lower error rates compared to the teacher model, with polynomial improvements observed in our experiments. Section 20, Number 20, Error Asymptotics. In this section, we explore the behavior of teacher error and its implications for performance generalization rates, PGR, in different scenarios. We observe that in our previous theorems, as the number of teacher features increases, the teacher error decreases, leading to improved PGR. This contrasts with language tasks, where PGR does not approach the optimal level but fluctuates instead. We present an example involving a linear network where the teacher loss remains constant as the number of teacher features grows. We also demonstrate that in the case of ReLU activation functions, we cannot achieve the desired error asymptotics in fixed dimensions. Specifically, if we consider certain conditions in our linear network assumption, we find that PGR can approach optimal levels under the right circumstances, even when teacher and student errors are both above zero. We then discuss the limits of weak to strong generalization. We show that while students can improve upon teachers, the best improvement we can expect is quadratic. This holds true for any two-layer model with a fixed random bottom layer and any activation function, as long as the teacher is well trained. Our findings indicate that the separation we observed in previous results is the maximum possible. Furthermore, we note that these limitations apply specifically to random feature networks. We highlight that even in these networks, while we can achieve strong generalization, we cannot have a scenario where the teacher performs poorly while the student performs exceptionally well. For the student error to approach zero, the teacher error must also decrease, and the student can only improve at a quadratic rate compared to the teacher. Lastly, we address the situation with ReLU networks, where the relevant basis for learning is spherical harmonics rather than input coordinates. We explain that the student can learn the teacher's coefficients more effectively for lower-order spherical harmonics. By correctly selecting the stopping time, the student can significantly reduce noise and achieve weak to strong generalization. We will further clarify these dynamics in the following sections. Section Summary. In this section, we demonstrate that while teacher error decreases with increasing teacher features in certain models, this behavior contrasts with language tasks where performance fluctuates. We also establish that for random feature networks, the student can only achieve quadratic improvements over the teacher's performance, and significant boosts in learning are not possible if the teacher's error is only slightly better than chance. Section: General Setup and Results. In this section, we present our results in a comprehensive manner. We begin by outlining our general setup and assumptions, followed by our main finding regarding weak to strong generalization. We also discuss a negative result concerning the limitations of this generalization. We define our notations first. We let the gram matrices represent random units projected onto or out of the top eigenspace. We introduce a key quantity that helps us understand the weak to strong generalization gap, which measures how well the teacher's features align with the top eigenspace of the student kernel. This misalignment is essential for achieving weak to strong generalization in our framework. We will drop the subscript when the context is clear. Additionally, we assume that the student's kernel accurately reflects the target function's prior, meaning the target function is supported on the top eigenspace with non-zero eigenvalues. We also assume that no two units in the teacher's first layer are linearly dependent in the first directions, which is generally satisfied for our assumptions. Now, we state our main theorems. For any ground truth and positive definite kernel that meets our assumptions, and for any teacher model that achieves minimum loss, we find that the test loss of the student can be bounded. Specifically, if there is a significant eigengap, we can choose an early stopping time such that the student's loss is a fraction of the teacher's loss. We provide a proof for this in the appendix. Next, we consider a 19-layer network with a bounded activation function. The first layer parameters are initialized randomly. We express the activation function in terms of spherical harmonics, focusing on the non-zero coefficients. For weak to strong generalization in a two-layer network, if our assumptions hold and the teacher achieves minimum loss, we can guarantee that the student, trained until a certain stopping time, will perform well with high probability. The proof for this is also in the appendix. We then apply our findings to ReLU and linear networks. For ReLU activation, we expand the activation function in spherical harmonics, noting that it can only represent functions of certain orders. We restrict the target function to be supported on specific spherical harmonics. Finally, under our assumptions for ReLU networks, if the teacher achieves minimum loss, the student trained to an early stopping time will also perform well with high probability. We provide the proof for this result in the appendix. Section Summary. In this section, we present our results on weak to strong generalization, outlining our general setup and assumptions, and demonstrating a key quantity that characterizes the generalization gap. We also establish a theorem showing that under certain conditions, a student model can achieve a significantly reduced test loss compared to the teacher model, particularly in the context of two-layer networks with specific activation functions. Section: Linear Networks. In this section, we discuss linear networks and establish a general bound for them. We note that if a certain space is covered by the first set of coordinates and if the teacher achieves the lowest possible loss, then for the student trained up to a specific time, we can be at least somewhat confident about the outcome. For the proof, we refer to the appendix. Next, we explore the limits of weak to strong generalization. We aim to prove a broader lower limit for student loss in these setups, including gradient flow as a specific case. We introduce the concept of shrinking optimality and demonstrate that the gradient flow solution is optimal in this context regarding its target function. We then present our main result, which indicates that the student can perform at most quadratically better than the teacher in weak to strong generalization. We define shrinking optimality. Given two functions, one is considered shrinking optimal with respect to the other if certain conditions are met. We will show that for gradient flow solutions, the learned predictor is indeed shrinkage optimal concerning the target. For any positive semi-definite kernel, time, and ground truth, the gradient flow solution is shrinkage optimal with respect to the target. We also show that both the teacher and the student meet the criteria for shrinking optimality concerning the target and the teacher's predictor. We then discuss the general limitations of weak to strong generalization. For any target with a unit norm and any teacher that is shrinking optimal to that target, along with any student that is also shrinking optimal to the teacher, certain conditions hold true. The proof for this can be found in the appendix. We also consider whether using multiple students instead of just one could enhance performance, similar to boosting. However, we find that even with multiple students, we encounter the same limitations of weak to strong generalization under similar conditions regarding the optimality of the teacher and student predictors. If the target is normalized, then for any teacher that is shrinking optimal to the target and any student with a smaller norm than the teacher, we observe specific limitations. Additionally, if we have a chain of students, where each is shrinking optimal with respect to the previous one, we find that certain conditions apply to the test loss of the last student in the chain. This includes cases where the student is trained using gradient flow with various stopping times and kernels. The proofs for these results can also be found in the appendix.